Okay. All right. Hello, everyone, and welcome. Thank you for joining us as we start the second half of our 2024 ISAR Virtue Aeolian seminar series. Philippe, Andrew, JB, and myself, along with the rest of the ISAR board members, are excited to continue this Virtue Aeolian tradition with Dr. Christy Swann. Before I turn it over to Philippe to introduce Christy, here's the structure of today's webinar. We'd ask that you please keep your microphone off until we get to the Q&A section. But feel free to type questions in the chat at any time. We'll get to them at the end of Christy's talk and read them aloud. Also during the Q&A, if you just prefer to raise your hand or unmute, that's totally great too, to ask questions aloud. This meeting is being recorded, and we will be sharing it with the ISAR community. We hope that you can hang out with us until the end, because we also have some exciting updates to share. And most importantly, we ask everyone to contribute to creating and maintaining a welcoming and respectful working environment that fosters diversity, inclusion, and belonging. And with that, I will turn it over to Philippe to introduce our speaker.
Thank you, Maddie, and thank you, Christy. So we have the pleasure to welcome Dr. Christy Swann for this webinar. So Christy, you are definitely an Aeolian person, right? Working on windblown sand, and especially you like a field environment because you like to develop technologies for various measurements. You did your PhD at Texas A&M University with Doug Sherman on the threshold for transport, and some of your instruments were also interesting for Mars, for measurements of transport on Mars. After that, you spent some time in the Ocean Science Division of the Naval Research Laboratory, also to develop technologies, especially particle tracking velocity system to measure atmospheric turbulence. And now you have started your own company, rCoast, also for field measurements, measuring coastal dunes change over time. And on the top of this, you are fascinated by the life of our hero, Ralph Bagnold. It's your hero, but it's also, in fact, our hero for the Aeolian community. So the rather unusual character who was, I will not spoil your talk, but with many facets and qualities, and we are very happy to have a good summary of not only his life but also his science. Thank you very much, Christy, and we are listening to your presentation.
Thank you, Philippe, and I just want to say hi to everybody. It was so good as everyone was coming on to see so many faces. I miss you guys. And it's so great to see everyone together. Whenever I was asked to give the presentation, Philippe and Maddie were thinking, let's start off with something about Bagnold. And for my dissertation, which seems like eons ago, but wasn't that long ago, I finished in 2014. I spent a lot of time decoding his work and re-deriving some of his theorems, largely associated with the threshold of motion, which I ultimately ended up doing my postdoc on and trying to build new instruments to really try to decipher this threshold of motion component for windblown sand. So I was really excited about the opportunity to start off this new series where we're going to just really talk about Bagnold, his life, the science, and his legacy, and what he has done for our community. And also, while I'm going to talk about his life, I do want to highlight some of the uses, the breadth of his work, but also some of the underlying assumptions that goes into some of the sediment transport models that are used pervasively throughout our solar system at this point. So thank you for having me. Let's see. So we all know this process very well. It is complex. It is difficult to measure in the field. It's arguably more difficult to even model the idea of wind and turbulence, mobilizing sediment transport and organizing that into streamers, as we're seeing here. And this is a video extraction of some code that I wrote to pull out the streamers from one of these videos. But trying to isolate all of that variability is our job. And that's what we've all chosen to do. And it's really, really complicated. And Bagnold started off, I think one of the coolest things about Bagnold is that he started off at this small scale and he ultimately reached this scale of large scale dune mobility and understanding of how that small scale process applies to this large scale phenomenon that we see. And we, from avalanching of dunes to ripple development to backing up into the even smaller scale to the mobilization of individual particles and electrification of windblown sand. What I'm trying to ultimately get at by showing you all of this is that the scales at which Aeolian processes work are, they are operate on a continuum. And it's really difficult to be able to decipher all of that. And I'm going to show one more video of streamers because I think they're really cool. This is some of our modern ways that we try to measure the three-dimensional velocity fluctuations of wind to relate that or associate that with the sediment transport that we see. But as we all know, there is significant horizontal and vertical variability of windblown sand. And so how do we quantify that? And even since Bagnold's first experiments, we are literally still trying to figure that out. So I want to bring us into Bagnold's world. This is a really short video of him going out into the Great Sand Sea. And it was this trip that really got him thinking about, one, how to navigate through the Great Sand Seas. This is in the Libyan desert. And also really started thinking about windblown sand. And all of us field folks that are on the call know that when you're doing field work, it takes a small army. And he had a small army that he was bringing out with him into the desert. Some of the things that they were doing were refueling, like having an airplane come in and drop fuel for them, trying to figure out how to get unstuck, redesigning Model T Fords, having to learn how to navigate, so much so that he couldn't use the magnetic compasses because of the vehicles. So he built the sun compass, which is now pervasive and was like throughout desert navigation. But he put that on all of the subsequent trips that he would go out with because it was a more accurate way to actually navigate the desert. So one of the reasons I love talking about that is because when you're doing field work, it almost is never as simple as you want it to be. You've got to build something. And so Bagnold, starting from the beginning, was having to build everything from scratch. Imagine not having the community that we do and having to figure out this very, very complicated problem. So I put together a little timeline of his life. He was born in 1906. And as he was growing up, his family's neighbor was had a laboratory in their home. And so he would spend his childhood building new things, which became a defining factor of the character of how he ultimately who he became to be and what he did for the Aeolian community. At age 13, he was started at the Malvern College, where he was looking even more into the science and engineering and really studying military for military applications. He signed up at 18 in 1914 for the First World War, spent a lot of time in France and Flanders. In 1919, he came back to Cambridge, spent 2 years getting a degree in engineering. In 1926, he spent a lot of time in Egypt, in the Libyan desert. Ultimately, that video we just saw was from the 1929 first, like true exploration, where he had a team out there and they started really kind of asking a lot of questions about navigation and windblown sand. So that trip spawned him going back to, which ultimately ended up being Imperial College London, for him to run a series of wind tunnel experiments. And so those wind tunnel experiments, as we're going to see in a minute, really laid the foundation from just some really small scale experiments for Aeolian sediment transport. In 1935 and through 1938, he actually did the publishing of many of the individual papers that ultimately would be wrapped up into the Physics of Windblown Sand book, where he added additional papers to that full publication. So his original publications, which are often cited as 1942, it was actually a 1941 book, but a lot of those papers are really from that were originally published between 1935 and 1938. After his wind tunnel experiments, he then knew he needed to go and test his theories out in the field. And so he went into his first experiment in 1938 and spent 8 days in the southwestern portion of Egypt running experiments, which I just showed a picture of on the intro slide. 1940 happened, World War II, he goes back to war. So he was in the long-range desert group leading navigation about that same time as whenever his book was published in 1941. About 1944, when the war was over, he essentially came back and was surprised that he was now this windblown sand guy and like was being asked numerous questions and to be able to talk. And he was inducted as a fellow to the Royal Society. And to all the PhD students out there, he did not get his PhD until he was 82 years old. And that was an honorary PhD awarded by RS University. So just know that a lot of work went into Bagnold becoming a PhD. He also, I think this date's wrong here, it's not 1944, but essentially he also established a really great connection with Luna Leopold, which is at the USGS. And he started exploring not just windblown sand, but fluvial transport as well as some nearshore work with Inman. And then fluvial to nearshore sediment transport. Then he worked with Carl Sagan to do windblown sand on Mars in their 1975 paper. And this was a huge pivotal moment because this is Bagnold really like becoming the sediment transport expert that we all know him as. The first predictions of windblown sand on Mars, like really nice experimental work that was done by Greeley and those, and they look back to Bagnold to help figure out how do they define the threshold of motion for windblown sand on this planet that it was very, very dusty. So it was 1978 that he was actually awarded an honorary PhD by RS at age 82. And then he passed, I think it was 1980. And then the Curiosity team in 2015 named the Bagnold Dunes after Bagnold for his foundational work. So I was going to do a Mentimeter where we can all see what do we think is more difficult? In the windblown sand world, do you think that arid landscapes are more difficult, or do you think it's coastal? And so as we think about that, I want you to hear it from Bagnold himself. So definitely turn your volumes on. This is from the blown sand interview that was done at RS for the RS Sand Project. And so this is their interview with Bagnold.
Indeed. The dune shapes were so much simpler than what one sees along coasts where there's been rain.
Oh,
if you get into the real waterless desert where there's no vegetation at all, one finds simple forms repeating themselves.
Christy, I also sent you the link to the slide.
If the wind
and
is
there's just
always more or less in one direction,
we have time.
One has the beautiful isolated
Maybe
forms of
log
the bark
on
ends,
really
like
early.
crescents, like crescent buns, moving forwards with their arms outstretched in the direction of motion.
So what you heard there was me also accidentally recording Maddie as we were recording this. So that's a new mashup, Maddie and Bagnold.
Yes, indeed.
So one of one of the things that I think is super fascinating is that Bagnold thought coastal dunes were too hard. And so he stuck with arid forms, even though he ultimately did move into the fluvial world and the nearshore world, and ultimately Mars as well. One of my favorite quotes of his time in the field is this one. I spent some very uncomfortable hours sitting in the open, directly exposed to a violent sandblast, trying to keep my eyes open while taking readings from an array of gauges and sand traps. The purpose of eyelashes was very evident. And anyone doing field work has definitely been in these shoes and experienced this. So going back to his initial publication that kind of defined and set the foundation for what we study, these are just some of the chapter names. And what I want us to note is how he starts from the behavior of sand grains, wind tunnel observations, understanding turbulence, and then confirming those measurements in a field experiment, figuring out the threshold of motion, and then coming with the unifying theory for the physics of windblown sand. And then slowly scaling up to what does it take for us to grow a dune from a bare surface? How do sand shadows and sand drifts behave? How do bark and dunes behave? Longitudinal or steep dunes behave? What is the internal structure of deposits? And he always was fascinated with singing sands. And the reason I wanted to outline these chapters that many of us have probably read numerous times is that if we took a poll right now, most of us sit in maybe 3 of these places. We're either a modeler or we're a modeler that does some field work. And maybe that's really focused on just at the surface, and we're looking at the interaction of particles with the surface. And that's where we can spend our entire career publishing. Or let's say you're working on dunes in, Namibia, for example. The scale of those landforms are completely different, and you can spend your entire career really looking at that large scale process. And Bagnold, in a series of experiments, ran through the entire gamut and wrote a book in a short period of time, in between his time between wars, to cover the breadth that is rarely found today. And so I just wanted to reiterate his ability, like with no community at all, besides referring to some of his fluvial geomorphology friends. He really started from the really small scale and blew that up to large scale processes. And I think that's incredibly important for us to remember. So what are some of the things that he provided us? So one, he didn't have a wind tunnel. So he provided us with the first consistent wind tunnel experiments. He built this himself. So from a young child, he was building tons of things and trinkets. And then in the Army, he had to build tons of things and figure out how to navigate. He came back to physically build a wind tunnel to be able to decode sand. We understand the threshold of motion and modes of transport, how those particle ejection angles and impact angles influence the saltation layer, where the concentration of particles lie and how that changes vertically. He even resolved the fall velocity for particles over time of varying grain size. This is another extrapolation of the saltation cloud height. And this is his experiments or velocity profiles and corresponding experiments from this wind tunnel on the threshold of motion. So this is how he derived what the fluid threshold was versus what the dynamic or impact threshold was. And there are a number of things I want to say about this. One, there's an unknown number of runs and an unknown averaging period to each of these measurements. I believe he had 6 profiles. Some of those profiles have 2 points. And we'll go through all of the things, but there are a number of things that if Bagnold was publishing this today, he would have a lot of responses and critique from reviewers for sure, because there's just a lot of uncertainty in this. But at the time, I mean, this was incredibly novel. And when it's tested in the field, it still works really, really well. So one of the things that is monumental in my own work with looking at Bagnold and really trying to redefine how we think about the threshold of motion is putting his definitions and his work into the context of others, and then also just from being in the field so much, like trying to piece together what the actual threshold really is. So we have his observations and his derivations from his work to have two different thresholds. The fluid threshold, and for those that are on the call that don't know, the fluid threshold is where a particle goes from, or a surface goes from no motion to now it's moving. And that's a higher threshold than your impact threshold, which is the lower threshold, and that's the threshold to sustain motion. So you already have windblown sand moving over a surface, and so it's the minimum speed before the motion shuts off. So that's your impact threshold. That's why it's lower. And it's about 80% of the fluid threshold, theoretically. In the field, and many people on this call I saw are field folks, we all know that that is incredibly difficult for us to actually identify from field observations. And one thing I want to note is that Bagnold was trying to figure out a way, when he was originally defining his threshold of motion, he needed his experiments to be repeatable. And the way that he could make a repeatable experiment is whenever the full surface was moving. And he called that 50% transport. So about half the surface is moving, but it was continuous transport. And the reason he used the word continuous is because as you slowly ramp up a wind speed in a wind tunnel, you have sporadic motion. So you'll have some small particles that are positioned to be able to become saltators, and now they're moving. That's technically, in Bagnold's definition, not the threshold of motion. And then as you increase the wind speed more, you'll have patches of the bed moving. And so you have a little bit more intermittency. And that's still below Bagnold's threshold of motion. And as you increase the wind speed even more, you'll reach a point to where the particle transport becomes continuous. And that is where Bagnold sat his definition. And he did that because it was the only repeatable way. It was too intermittent and uncertain in the beginning. So it's just a really interesting point for us to all take in, that this definition from Bagnold was, one, a visual observation. So there weren't sensors. He had a camera in there and created a light sheet to be able to visualize the transport, but there was no way for him to quantitatively, besides visual, define that threshold of motion. All that to say, even with that uncertainty in the definition of the threshold of motion, the fluid threshold of motion, his model actually still does pretty dang well in field experiments. So here are just a couple things about those original experiments that we just need to know as we move forward using Bagnold's threshold. And I focus on the threshold because that's where most of my work sits, and I just have spent a lot of time deciphering it. But there was no separation of modes of transport, and that's totally fine. A lot of times in fluvial, bed load is all wrapped up into one. There's the visual demarcation. We also have an uncertain number of the actual velocity profiles. And some of those profiles were 2 points, some were 6 points, I had mentioned before. And so, that there's just uncertainty in that. There were no statistical estimates on the uncertainty or confidence limits in his predictions. And there was uncertainty in his extrapolation of K prime and Z naught. So, and there are a couple other things where Bagnold, just between his publications, would change his values sometimes, and they were a lot of times embedded in the footnotes. even with all of this uncertainty, Bagnold's model is still pretty good. There's also an interesting parallel that I found in my work where Bagnold is trying to find fluvial folks back in the 30s so that he has some kind of community to figure out, like, how do I define the threshold of motion? So all of the, that continuous motion definition, that was from the work of Kramer, which is a fluvial sedimentologist in Germany at the time. Also, at the same time was Shield. Shield was coming out with his way of calculating threshold of motion, largely a function of buoyancy of a particle and the particle Reynolds number. Bagnold, even with his derivation from his experiments, is essentially the square root of the Shield's parameter, even though the derivation does not include Shield's parameter at all, but it's just a really interesting note. So after Bagnold spent a ton of time figuring out windblown sand, once he got back from World War II, he really started focusing more on fluvial transport. So he had developed a relationship with Luna Leopold, had come over to the United States, and they had built a flume together and did a whole bunch of flume experiments, and then went and tested that in the field in a river in Wyoming. They actually modified the river and did some field experiments, and a lot of that work is really about the relationship with stream power and depth in relation to sediment transport. But he did a ton of other things and started trying to combine and build a universal relationship for the relation between sediment transport by wind and sediment transport by water. Also, he published with Inman, and this is in a book where they were figuring out sediment transport in the littoral zone. So it wasn't just the fluvial world that Bagnold stayed in after he came back from World War II. He also went into the nearshore. And then he started publishing with Carl Sagan. And so this was like some of the extrapolations between sediment transport that we know, that we've learned from fluvial processes and Aeolian processes, and translating that to Mars, which ultimately the folks that really started using Bagnold for predicting the blown sand on Mars, that was largely Greeley and Iverson and Bruce White back in the late 70s and early 80s, in defining that threshold of motion via a set of experiments where they worked at the NASA Ames wind tunnel, reduced pressure down to the pressure on Mars, and figured out what that would be. And whenever Greeley and those folks were actually building that threshold of motion model, they also didn't know how to define the threshold of motion. And so they too used the visual demarcation of continuous transport over a surface. So I wanted to show us where Bagnold is now. Bagnold may no longer be with us, but he has dunes named after him on Mars. I just published a paper with my colleague Matthew Lepope and others where we were looking at ripple wavelengths on Mars from observations, trying to figure out fall velocities. And so it's just been really, really interesting work. And here's just a close-up video of some of the Bagnold dunes. So this is windblown sand on Mars. You can see the different scales of feature. You can see the crusting of the surface. You also can see coarse grain lag deposits on the surface. And so in a second, you'll see where the rover wheel is exposing finer grain particles. And on the underneath, you have the finer grain material, while on the surface, you have the coarser particles. This is a classic coarse lag deposit that Bagnold would talk about in his early work. And same process happening on the red planet. So the proliferation of his work spanned small scale to large scale theoretical observations, theoretical models, wind tunnel observations, confirming that with field work, both with wind and water. And ultimately now his work is being applied to Mars. And whenever we tested out the models that perform the best, Bagnold's threshold of motion model performed the best on Mars with a correction factor. So that is an overview of Bagnold's life, his science, and his legacy. And so this is just a, you know, a really incredible person that kind of stumbled into windblown sand and then ultimately became the father of Aeolian geomorphology. And his work is pervasive, not just for in arid environments, but in coastal, fluvial, and now on Mars. And so that's it. I'm happy to take questions and chat about Bagnold. I also would love for folks to provide their own input of Bagnold's favorite quirky thing that you've heard. I'll start with mine, which is in one of his experiments when he was going out to the desert, he was trying to see and measure how fast a sand grain was moving. So how fast the saltation cloud was moving. So he got in his Model T and he drove as fast as he could to see if he could try to keep his eyes on the particles themselves and get to the same speed of the saltation cloud. That's one of my favorite anecdotes. But anyway, happy to hear yours. We all know a lot about Bagnold, and yeah, happy to talk about him some more.
Thank you, Christy.
Thank you.
Feel free to add questions to the chat, or if you want to use the raise hand function and unmute, we would love to hear from you as well.
Maybe I can start with a question, then it will help people to start also. So Bagnold was not an academic person in the sense that he was out of the usual environment, right? So he was a soldier first. He was an engineer. He was not exactly in the ordinary track system. And so my question is, where did he get funding for all of this all of this work? Do you know this? I mean, today we have grants and everything, but in the past it worked differently. But how was it for him?
I don't know the answer. I know that at one point he was having his team document really carefully all of the expenses that they were they had, and then they were getting reimbursed for it later. So I do know that. I think he was funded. I can't remember if it was Royal Society. He became a fellow, so he likely had access to some funds through that. But Jeff Lee might have a better answer. Jeff has done a lot of work on Bagnold as well, as I'm sure many other folks on here know too.
All right.
I do not have an answer.
Other questions, dear audience?
I'd like to get others' thought on this, but I've always thought that Aeolian geomorphology greatly benefited from having an engineer basically found the science. And it really helped us get into quantitative assessments, which were pretty rare back in the first half of the 20th century. So I'm just curious if anybody else has thought of that or wants to comment.
I feel like for us field folks, we're constantly having to build a new method, a new way of measuring something, or we've figured out this. And Bagnold, having built his own wind tunnel, built the first bedload trap, built a portable manometer, redesigned or re-outfitted Model T Fords. Like, he had to redo almost everything and build everything he needed to be able to answer the questions that he had. And yeah, it's super inspiring. I've built a lot of stuff just because it feels like we came from the capability. Like, if you don't know it, or if you can't answer it, then build something to solve the problem or to answer the question.
I see a raised hand from Matthew. Go ahead, Matthew.
Yeah, thank you, Christy. I wanted to ask the last few slides you left us with were in Gale Crater and some remote observations from the rover. And I'm not familiar with the latest work that you and Matthew and colleagues have come up with, but I'm interested in finding more. But specifically, I'm interested. Matthew's talked a lot about the wind ripples that are centimeter scales in terms of wavelength. And then all over Mars, all over Martian dunes, we see meter scale wavelength, large ripples, or dark large ripples that have been called that. But then meanwhile, you can view a continuum of into what we think are mega ripples viewed in high-rise images and other remote observations where wavelengths of 20 meters and 30 meters and 40 meters and almost a continuum. What would Bagnold's physics talk about, if anything, about those types of bed forms and in the conditions we see on Mars?
You know, Mars is while I've ran experiments at NASA Ames in the low pressure wind tunnel at Martian pressures, there's nothing better than understanding a process when you can stand in it and you can physically be there. And on Mars, none of us can do that right now. So we have robots that, you know, you've been a part of these teams that are doing that. And that's incredible. I think that we just published the paper about the emergent wavelength of ripples on Mars or mega ripples on Mars. But I think there's a lot more for us to figure out. When you have such a low density surface, that means that the kinematics of the particle impacting a surface and how much energy that's retaining, it changes the dynamics of saltations. It changes the height of saltation. The boundary layer is different. So I think us being able to like solve that problem, we need a lot more field experiments physically on Mars so that we can refine that. I was working with Claire Newman and Swann and another group to try to build a set of landers where we can try to get better observations of the boundary layer as well as measure sediment transport and the saltation profile on Mars, because I think that's huge. And we have, you know, the Almeida and others from 2005 that, you know, predict that we have massive saltation or giant saltation on Mars. And then we have, you know, some observations where it doesn't seem like some of our theories of how we define the threshold of motion don't really work very well on Mars. We see particles moving along that surface by just rolling. We see, sediment transport below the threshold of motion. So I think we need a lot more field experiments to be able to really tease out the dynamics of how that surface is moving.
Excellent, thank you.
Thank you, Matthew, for the question. I think Andreas is on and has a question.
Hello.
Hi, Andreas.
Hi, Christy. Thanks for that enjoyable talk. That was very nice to see some of those quotes, and the footage is really cool to see that from almost a century ago now.
And you can there's a new the video was released, I think it was 4 years ago now, by Royal Society. It's like 50 minutes long. It's completely silent. It's just really cool to watch, and it's the 1929 focus, that expedition out there with his team. So that was just a minute clip, but there's so much more. And as like folks who also are fascinated by Bagnold and what he was doing, like I highly suggest go watch the whole thing.
Yeah, absolutely. I just actually wanted to connect back to Jeff, who was making this really interesting point that we as a science have really benefited from Bagnold initiating that from an engineering kind of context and a methodology that is really rooted in quantifying and measuring things, because it does strike me, thinking back at what we know historically, developing particularly on the geography side at that time was really mired in this completely unproductive geographical cycle theory proposed by Bill and Morris Davis, which was essentially an intellectual dead end. And Gilbert, who was working in rivers just before Bagnold, I think, who was also a much more of a quantitative geomorphology, was sort of sidelined for a long time. I actually don't really know enough about fluvial geomorphology to get a sense of what they were doing around this time. My sense is it was probably much more descriptive, maybe a bit more regional focused, just kind of describing landforms rather than trying to measure things. I don't know if anybody knows what fluvial people were doing at that time.
Well, in the 1930s, so Bagnold referenced the material that was being done by Kramer and Owen. Owen was back in 1908, but these are fluvial guys. And he essentially tried to copy their flume experiment and do that for wind. So build the same kind of setting. And there were visual observations. At least most of my expertise in this area is about the threshold of motion. So they were redefining the threshold of motion in stages. And so he was really leaning on their work. I don't know about the quantitative measurements though, but someone else, please jump in if you know that.
Well, I don't know if I know a ton of the details, but particularly his work or the time he spent with Luna Leopold would have been very quantitative focused in fluvial geomorphology.
Yeah, but
And
that was
at the time,
the 50s, wasn't it? That's
yeah, that was later on,
after
50s,
the geographical
60s.
cycle has finally been binned,
Yeah,
and people sort of actually start measuring stuff in all of earth sciences, really.
I'm pretty
Yeah.
sure Leopold's degrees were in civil engineering.
Yeah. And I mean hydrology, very heavy in hydrology. Yeah.
Anyway,
well, he built a flume with Leopold, like at USGS. Bagnold built a flume with Leopold, and then went and did the experiments in Wyoming where they modified a stream to test out what they had seen in the flume.
Yeah.
In Bagnold, also like part of his like physical instrumentation, so the threshold of motion was visual, but he also had to each different section of his wind tunnel, he had a load cell attached to it so that he could try to see how sediment transport was occurring along the wind tunnel. I mean, now we know a lot more about flow dynamics through a wind tunnel and trying to get an equilibrium profile and tripping the boundary layer and all of those things. And there's a lot of uncertainty in like how that physically happened. And he also built a portable manometer. So I know that he had a manometer and he was looking at readings from the manometer in the wind tunnel that he had, but then he built the portable one for his wind tunnel measurements, his field measurements in 1938.
Yeah. Cool.
Colin, question.
Sweet, thank you. Great talk, Christy. I was just wondering how Bagnold tried to tackle the problem of roughness height. How did he get it at Xenot? How has that changed over time? Is it still as applicable as his sediment transport equations? And is there anything particularly funky that may change things with your work on Mars?
That's a hard question to answer. So with Xenot, so Bagnold used the classic d/30. So he assumed it was, aerodynamically smooth. With the roughness height, there was the K prime, which was the adjustment. And so that was him kind of accounting for some of the saltation concentration, which is different. But he knew there was such modification at that height that he wanted to extrapolate to zero there and then do a linear extrapolation within that high concentration of particles, because that's where you had a more linear velocity profile. On Mars, Xenot is very different from Earth, because what happens on Mars is because of the atmospheric density and the viscosity, you have an expansion of that viscous fluid layer. So a lot of the particles actually sit below that. And so it's a very tricky area, and I don't have the answer for it. I know Nick Webb and their group have done, I know Nick's on the call, he's done a lot of work on Xenot in arid environments. One thing that I, and what I did, gosh, it's been so long, but I calculated the protrusion, like how tall the viscous sublayer was and the particles were protruding from that. And one of the things that always gets me when I think about Xenot is, you know, as you have these big turbulent gusts that are moving. So anytime you're out in the field and you're feeling these pulses of you know, gusts, that's like changing or modifying what's happening at the surface. And so I think that on Earth it's really hard for us to pin down, but I think on Mars it's even more difficult, because now I think that you would get a fluctuation in the height of that sublayer where you have the submersion of particles or the exposure of particles. And so it's not this really beautiful linear easy thing to model that it's this, you know, height above the surface. So we know on Mars that it's not d over 30. We know that the particles are submerged within that. But without field measurements, and also measuring Xenot is always going to be an extrapolation, because once you start actually trying to get the pressure fluctuations inside a particle, then you're messing with the flow around it itself. The Irwin sensor, which was developed by, I want to say that was Jack Gilley's group, or maybe they just used the Irwin sensors quite a bit, but essentially that was one of the ways that they were trying to figure out what that relationship was.
Cool, thank you.
So I wish I had a better answer, but Xenot is tricky. I think Xenot is an incredibly tricky parameter to try to define.
Thank you for the question, Colin. I guess I had one other follow-up question to what Jeff and Andreas had brought up in terms of his background as more of an engineer, but in how him collaborating with other folks as well. I guess we kind of think of Bagnold's career of, like, you know, expanding in different environments of what systems he's interested in, and kind of connecting across Aeolian, fluvial, marine, Mars environments. But also it also makes me think of work that a lot of people on this call, I think Joanna's still on here, but like the interacting processes. Like there's a great picture of Bagnold and Luna Leopold, you know, rafting down Cataract Canyon, which obviously has a lot of like fluvial processes going on, but from those deposits, you know, there's a lot of windblown processes as well. Sorry, this doesn't have a very direct question, but just thinking of, you know, the Aeolian processes have a lot of similarities with fluvial processes and others, but also that we just have environments where we have these interacting processes, and you kind of need to think about them both. And you can learn from like the different backgrounds, the different knowledge, but also that they just do interact as well. I don't know if anyone had a follow-up comment or thought on that.
Well, just a follow-up comment on that. I wonder if whenever he wrote the paper, sediment transport by wind and water, I think, or water and air, I forget what the exact title is. I had it in my presentation. I wonder if that was stimulated by him being with Luna Leopold in that environment where you have both these lithified Aeolian features, and then you have the beaches that are the you know, sand and available for windblown sand, and then you have the river there. I'm not sure. Would love if someone else knows that. I don't know.
Maybe we should you know, follow Bagnold's path more closely and work better with the fluvial community. You know, we say we are the Aeolian community, but you know, Bagnold would disagree. You know, he would not subscribe to ISAR, maybe, because he would like maybe to gather also the fluvial community and to make more bridges between us.
Yeah, I mean, in most of his, like, he's known for windblown sand, like, especially to us, because that's all where we focus. But he really only studied it for like a very short period of time. Like, he did not spend his life studying windblown sand. He was exposed to an environment where he was amongst it and in it for a really long time. But then once he got back from World War II, like, he was really like doing a ton of fluvial work, and then also some windblown sand. But he transitioned, you know, and so it's just a really interesting take that one, in just a short period of time, that one individual was able to cross scales, tease out so many of the underlying mechanics, and that his models actually still work with minimal observations and that insight without a community. I just am so impressed by that. Like I would not have the knowledge that I do without like everybody on this call, like talking to at conferences and us reading the same papers and, you know, us building off of the folks that were doing it 10 years before us. Like that is how we build as a community, and Bagnold didn't have that. He had fluvial folks. And so it's just incredible what he was capable of doing in that short period of time that he actually studied Windblown sand.
Yeah. So let's maybe take this last question from Joel in the chat. Christy and the rest of the group, if Bagnold were still with us today, what would he be working on?
Singing sands. The last chapter of his book is about singing sands. I think one of his last papers, he wrote about it again. Like, he was so fascinated by dunes making sound. He talked about the sounds of windblown sand. And so, you know, whenever we're writing an NSF grant, if he ever had to do that, or a NASA proposal, I don't know what the broader impacts of singing sands would be, but I don't know. That's what I would think.
Thanks for the question, Joel. So Christy, do you mind sharing your that slide one more time while we wrap up here? Thanks everyone for being with us till the end. We hope that you enjoyed the most recent edition of the ISAR newsletter that just went out. And if you didn't get it, that's okay. I think you can get the latest copy on our website, which is at the bottom link there, the aeolianresearch.com. Thank you so much again, Christy. This was a wonderful talk and conversation.
Thank you.
And thank you guys so much for having me.
Yeah. And we look forward to our next couple of talks in November, December, and then in January. Keep checking our website for more information for the registration of the links. Also, make sure that you go to our website because Alex Hall, who's on the call, has been doing great updates to our website, and we have a new membership process. So everyone does need to create a new account, and then you can update your membership on the website as well. And this is the way that we're going to be sending out the newsletter from now on. So please, please, please do that in the very near future so you don't miss our future updates and just community messages that are going to go out through that system. If you have any questions, you can reach us at the admin@aeolianresearch.com. That email is also on our website. I just want to say thank you again to everyone who was able to join today and ask some great questions and have a great conversation. And we look forward to hopefully seeing you for our next couple of talks. And with
thank
that,
you, everyone. Thank you, everyone, also. And I hope to see all of you for the next talks. Thank you.
Yeah. I'm going to pause the recording and we can keep talking about Bagnold for anyone who else wants to stay. So thanks.